End of the day, end of the week, it's just too much. Huh? Yeah, but no, no, it's end of the week for me because they don't come on Fridays. I don't have to teach on Fridays. So.
Yeah, I mentioned that.
This is the end of the week. Thank God. Okay. Everybody doing all right? Everything going okay? Nothing. Yeah, nothing bad. Okay. All right, good. Okay, so what we've been doing, just to remind myself, has been to try to quantize a field theory, right? And what we're interested in is not just quantizing a field theory, but in particular, we want to compute things like cross sections or differential cross sections or scattering amplitudes or whatever, right? And to do that, we've derived a way to go from a quantum field theory, or go from a field theory such as the real Klein-Gordon field theory, to something physical like the scattering amplitude, which we typically call the S matrix. Okay, and so to make that kind of jump from the field theory to physical observables, we've developed this equation called the LSZ formula, right? And we saw a couple classes ago that this not only works in a simple non-interacting theory, but as long as we incorporate some conditions on our fields, we can also use it for interacting field theories, right? And those conditions were that the VEV vanishes and that the single particle states have the correct normalization, right? And if we come to a theory and we compute those two quantities and we see that those two things aren't true, then really all we have to do is either shift the field by some constant and or rescale the field, and we're able to tune our parameters such that that LSZ formula is still valid, right? And so the main thing that we're after, because we all know how to take derivatives and integrate, the main thing we're after in that first equation on slide 2 is the correlation function, which is basically the last line. So we'll call it the correlation function. We'll call it time ordered product of operators and some other stuff. Okay, but just know that it's that thing sandwiched between two vacuum states. Okay. So what we did last time was we said, well, let's not get crazy and try to tackle the full problem all at once, but let's take baby steps, right? And so the first baby step we took was to calculate the transition amplitude or the propagator, and just a particle, quantum mechanics, a quantum mechanical particle, right? And the way we do that is we use, we could do it in the canonical way, but we want to use the path integral formalism, and so that's what we did. So we developed techniques going through slides 7, 8. We developed ways to compute the path integral, what we ended up calling the path integral, okay? And it's just basically a sum over all paths of e to the I action, right? And you say, that's great, it's a beautiful result, it's something to put on a postcard or whatever, right? But at the end of the day, you want to be able to compute something, right? So we said, well, let's look into this in more detail. And so what we did was we developed basically kind of an algorithm or a list of mathematical tricks to compute things that we're interested in, which is namely the correlation function, right? That's what we're after at the end of the day. So we started looking at basically matrix elements of the big Q operator, the big position operator, right? We use big Q to denote an operator and little q to denote the eigenvalues, right? And so we started to look at this thing in terms of the path integral, right? How we develop the path integral. And we see that if we're looking at matrix elements of big Q, right, we end up with things that look like the path integral with just some numbers shoved in there in the integration as well. Right? So we could use that in the reverse way and say, okay, if I'm interested in computing, the time ordered product of two operators, I could use, whatever it is on the left-hand side, where you have two position numbers, as a function of these time parameters inside the interval. Right? And so then we said, okay, well, how are we going to do this? How are we going to use this idea or this concept? And so we developed a way using functional derivatives. Okay, so functional derivatives are derivatives of functions that depend on a parameter with respect to that same function with a different parameter. Okay, and the answer is when you take those, when you take that derivative, it's just a Dirac delta function in the time parameters or in whatever parameters your function has. Right? And it's just in complete analogy to the normal derivative that we're used to. Okay, so we said, okay, well, how can we use this functional derivative trick? And the answer is we can shift the Hamiltonian, right, by what we might call external forces. Okay, in other words, we're shifting the Hamiltonian to include some auxiliary terms, right? And you say, well, what is that good for? Well, it's good because we can use these functional derivatives to basically pull down factors of the little q, right, inside of our integral, inside of our path integral. Right? And then that we can relate to these correlation functions that we're after. Okay? So that's what we did. So we were showing how if you take functional derivatives of the path integral with the Hamiltonian shifted by these auxiliary terms, you can pull out factors of the Q quantum number, which we can relate to time ordered product of Q operators, right? And what else do we do? So that was one trick, okay? And then the other trick is we want to simplify our lives by considering the initial and final states to be the vacuum state, right? And that just, so the way we did that was to basically argue that, you know, we're interested in the limits where the initial time and the final time are very far apart, so we can take those to be minus and plus infinity. And then if we insert a complete set of states of the Hamiltonian, right, we use that idea, we take those limits, we end up finding that all the states drop out if you do this other trick, which we call the I epsilon trick. Right? If we shift the Hamiltonian by some small imaginary part, which in the end we're going to take to 0, so we don't, you know, affect the physics. But if we do that, in the middle, or in the what's the word I'm looking for? In the process of doing that, we would see that, you know, all the other terms, all the other states drop out of this linear superposition for our initial and final states. So not only are we shifting the Hamiltonian for the functional derivative trick, but we're also using this trick where we shift the Hamiltonian by some small imaginary part. And that allows us to just consider the ground states, or the vacuum states of our initial and final states. Right? And that comes into play. That's important because what happens is, as we saw, when these terms go away, right, when the auxiliary terms go away, this guy is just 1, right? It's a transition amplitude between the vacuum state and the vacuum state, right, in the absence of forces, and that's just 1. You're not going to change the state if you don't apply any forces. They're stationary states, okay? So that was why we did that. And then we said, okay, so now we've got kind of an idea of how we can go about computing these correlation functions once we're given a Hamiltonian. Right? And we said, okay, well, you know, this was all for non-interacting theory, but we want to consider interacting theories, okay? And so the way we're going to build up interacting theories is using perturbation theory. Right? So we write our Hamiltonian in terms of a non-interacting piece. In other words, the simple piece is the term that we know what the solutions look like. Or in this term, we know, or in this case, we know what the path integral is. Right? Plus some small piece. And that small piece is what we're going to take perturbative expansion in. Okay? And so we wrote down our new Hamiltonian, our new path integral, right, with h0 and h1 in there. And then we said, well, if h1 is only a function of p and q, we can actually use the functional derivative trick to build this term, right? So we can actually build it by writing it not as a function of q and p, but as a function of these functional derivatives, right? And if we do that, and we keep in mind that the way those functional derivatives, how they work, they just basically bring down delta functions or bring out delta functions. I can pull all that stuff outside of the path integral, right? So now I've got some operator, that first exponential in equation 42, operating on my path integral with auxiliary terms. Okay? So I've separated out the interaction piece from the non-interacting piece. Okay? And we said there's always some conditions. H1's only going to depend on Q, and we're only interested in time order products of big Q's, and H is not going to be any more than quadratic in P. Okay? Those are all just physics arguments. Okay? And so if that's the case, then we can reduce equation 43 down to something that looks like this, where I've explicitly written out the Hamiltonian, because that's what we'll be working. We'll be working with the Lagrangian, right? And so if we're not interested in any time ordered products where we have P's, big P, then we can drop the HP term, right? And then, like I said, there's a typo. The first line shouldn't have that functional derivative with respect to H, because we have no H left now. Okay. All right. Okay. So this is where this is our starting point for an interacting theory. All right. Once we're given the Lagrangian along with the interaction piece, we can go off and construct this guy, and then we can start to think about how we're going to construct these correlation functions when we want to compute the S matrix. Okay. So then we said, okay, now we've got a kind of a skeleton, formalism, right? Let's try to apply this to a particular case. And so we looked at the harmonic oscillator, quantum mechanical harmonic oscillator. So we're still in single particle physics here. We're not really doing anything in field theory yet. But we're going to use all the tricks. We used all the tricks that we learned. In other words, we shifted the Hamiltonian by some small piece, by some small imaginary piece, right? And we got something that looks like equation 47. And then we said, okay, now what do we do, right? And we guessed a couple of things, that we try to do, like we tried to guess the Gaussian, all of our other, usual guesses, and nothing worked. So we had to do take a Fourier transform, okay? And so when you take a Fourier transform, what it does for you is you had to do a little bit of math, right? But it pulls out the factors, kind of separates out the factors of t. So if you go to equation 54, after we've plugged in all this stuff, we've taken Fourier transforms, and you see the only t dependence is coming from this exponential. And that exponential, when you integrate over it, just gives you a delta function, right? So it's a delta function in E and E prime, the two energies that we had, the two energy variables that we're integrating over. And then we can use that delta function to do one of the energy integrals, right? And then we said, okay, let's see if we can simplify this more. So we rewrote the terms in the square brackets, assuming that, or knowing that e squared plus omega squared is a constant. It's multiplying this epsilon. Epsilon we're going to set to 0, so we can just absorb that. So that's where it goes away. That's how it goes away. And the action then simplifies, right? Then we do a change of variables. I'm going through this because we're going to do the same thing today, but for a field theory, okay? So we do a change of variables. We do that change of variables, and what happens is we get a nice separation between our auxiliary terms, the external force terms that you might call. So you look at equation 63 here, and you have this exponential out in front hitting or operating on or multiplying the path integral in the case or in the limit where there's no auxiliary terms. Okay, and like we said, that guy is always 1, right? So in the end, we can write the path integral for our theory as equation 66. Okay, so it's just the two force functions, if you will, right? Divided by some term that we're going to know or come to know as a propagator term. Okay, propagator denominator. Okay, so we got something that looks like that. All right, and at that point we said, okay, let's go back to our original time space. Right, so we plug back in the reverse Fourier transforms, and we get something that looks like equation 67. Where you have this g function, which we came to know as the Green's function, being sandwiched between these two f terms. Okay, so we've got our path integral, and it's written in terms of these f functions, Green's function. I'm not going to go through the computation of the Green's function again, but it's there, right? Typically, we don't worry about it, okay? So we've got our, let's go back. So we've got our path integral, right? And we've said that to compute time-ordered products of operators, we just take functional derivatives, okay? So if I'm interested in the time-ordered product of two operators, Q of T1 and Q of T2, I just have to take two functional derivatives of that path integral, right? And we saw at the end of class what it does is it basically, you have to go through some math, right? And like I said, if you're interested in this, it's good to practice because, we'll do quite a bit of this today and in the homework. Well, you guys know the homework that was due today. Right? You guys have already, hopefully you've already. So you have to take all these functional derivatives, but in the end of the day, you know that you're setting f to 0, right? So when you start seeing these terms, where you have f's left over, and you know that functional derivative, when it hits it, it's going to still leave over a factor of f, you can start dropping these terms. So you don't have to carry out all these functional derivatives. You can use your, your intuition, you know what I mean? Okay? Just don't go too far, you know what I mean? So in the end, so the 2-point, what we would call a 2-point function, like I said, these things start getting more and more names. Okay, so we started out with correlation function, time ordered product of operators, and now I just call it a 2-point function. Okay, but the 2-point function, the time ordered product of two operators, is just proportional to Green's function. Okay. And so you can go on and you can compute these things to blue in the face, right? You can compute 3, 4, 5, 6. Like I said, the qualifier problem I'll give you will have 45 numbers of Q's, right, that you have to compute. But the thing right at the top of your head is that if I have an odd number of operators that I'm trying to compute, I can just set it to 0, right? Don't be one of those schmucks that didn't take this class, and so they didn't know that, okay? And you can tell them I call them schmucks, okay? And it's 0 right off the top, because no matter how, after you take all these functional derivatives, every term is going to have a leftover f, right? And so when you take f to 0, all these terms go away, okay? So you only have to worry about even numbers of q's, right, for your time ordered product of operators. Okay, and so in general, you could go up to however many even Q's you want, and what you find is that they basically pair off. Okay, so like I showed you the case of 4. Did I do it in here? No. So I showed you the case of 4. It's just basically 3 terms where you sum over the pairings of these guys. Right. So it's a 2-to-2 function or a 4-point function. It is a sum of 3 terms, and each term has 2 Green's functions in it. Okay? Okay, so that's where we stopped last time. Any questions on that stuff? Sweet. So you guys are experts. So I'll skip the next the next lectures, and we'll get into Okay. All right, so by the end of the semester, I want somebody to get this tattoo. Okay. What? Come on, this would be so cool.
Yeah, but I don't do tattoos.
Okay. How about you get it like shaved into your head, maybe like a Feynman diagram shaved into your head?
Probably not.
No. Okay. Well, all right. If you want to get a D, that's up to you. No, I'm just joking. But you can't get the tattoo. I would give you extra credit. I'd give you like 5 points extra credit. Okay, and it has to be real. It can't rub off. Okay, we have to have documentation of you getting the tattoo. Okay. All right. So everything we've done has been for either single particle quantum mechanics or classical field theory. And now what we want to do is we want to work on quantum field theories, okay? And to do that, we're going to use the path integral formalism. That's why we spent the past couple of days building up to this point. All right. But the good news is we're going to do the same things that we did when we studied canonical quantization. Like I said last time, we've already done a lot of the heavy lifting as far as the math goes, and so we can just make some easy changes. Okay. So some of those easy changes would be to write down the path integral. Okay. So this is so first we go from single particle quantum mechanics to multi-particle quantum mechanics. Right. This is like what we did in the very beginning of this semester. Right. We started with the physics of one particle, then we went to multi-particle systems, and then we said, when we get to very many particles, it's good to go to almost a continuous limit, right? And that's when we studied the, what's it called, the infinitely long elastic rod or whatever, okay? So we would do the same thing. So we'd start out with single particle physics, the expression that we had before, and we'd replace that with multi-particle physics, right? And the changes we need to make there is that now we have to sum over the Lagrangian of all the particles. Okay, so we don't just have a single Lagrangian anymore. Notice that every particle has its own source term. That should be an A right there. So this is every particle has its own source term. Okay, and if you go through and you follow what we did before, you'll find that the path integrals, now you're going to have a product of all the path integrals. Okay. All right, so luckily we're not going to work with that right now. We might do some of that when we go and study condensed matter or solid state physics, right? But what we're going to do now is apply field theory, okay? So let me take that case and now go to the continuous limit, right? So when I go to the continuous limit, I replace things like the eigenvalue or the C number Q sub A, I replace it with a field. A field. That's needed to change the emphasis on how I'm saying that syllable. Okay. So we're going to go from a point to a field, right? And so it's going to get a little confusing because you're just going to have to. What do they always say in books? You'll know it by the by the use, by how it's used, right? So I'm going to use the same variable to represent a C number, like an eigenvalue, and an operator, okay? So you'll know, like, when you see it, oh, he means operator, or he means eigenvalue, okay? And so we do the same thing for the momentum, and then we make the other normal continuous, when we go from discrete to continuous, we replace a sum with an integral, and this guy becomes not the measure over QA, but now the measure of the field. And then the big thing that we're going to change is this F term. Okay, so now we're calling these guys force terms. Okay, now we're going to call them source terms, and this is more fitting or more correct when you're talking about field theory, and you'll see why. Okay, so F of A is going to get replaced by a big J. Okay. Okay, so when we do that, our path integral, or what we're going to come to know as the generating functional, okay, Z0, which is our path integral, is going to look something like that. Okay, so all I've done is make the replacements that I talked about before, right? And it basically looks exactly the same as what we had, okay, except, Q's have turned into phi's, and F has turned into J. Okay? Now, like I said, we've done all the heavy lifting, so I'm basically just going to outline, we're going to take the same exact steps. Right? The only difference is, well, I don't know where the differences are, but we'll see, okay? All right, so the first thing I want to do is put the Lagrangian in a particular form, okay? So we start out with the Lagrangian for the free Klein-Gordon theory, right, that you should be able to write down on a piece of paper anytime I'm like, write it down, and you can write it down, okay? So you should be able to write this down, right? And then what I want to do is use integration by parts, okay? So I want to move one of these derivatives onto the other one, right? So I get something that looks like del squared, right? Because what I want to do is I want to write it in terms of the Euler-Lagrange equation of motion operator, okay? And so when I do that, I would get not only the two derivatives on one of the fields, right? But I would have another term with a total derivative term. So I would have a term that would look like del mu operating on phi del mu phi, right? That would be my other term that I haven't written down, but I know that it's inside of that integral, right? And if it's inside that integral, it's a surface term, right? D4, D4x, right? And so this thing is just going to evaluate to phi del mu phi, right? Just using the first theorem of calculus. And so this is a surface term, right? And I'm assuming that the fields vanish at the, the correct boundary conditions, right? That you normally apply in quantum mechanics, okay? So that's what I mean here in blue when I say integration by parts, and I've dropped the surface term, okay? So at this point, I can rewrite this guy, and it looks like this, okay? Where I've just now del squared. If you want to be, explicit about it, you can put an arrow that points to the right. Okay, just to remind yourself. So you'd have del squared, and it's not really a vector anymore, but just to remind yourself. Because remember earlier you guys got confused when I wrote something that looked like that with a point to the left. Okay, but just know now it's operating on the right, to the right. Okay. All right. So I've got my Lagrangian, right? And now what do I want to do? So now we go down our list of when we're stuck, what do we do? Right? And the thing that we come across that works is to take a Fourier transform. Okay? And same Fourier transform you used before. It's a little more difficult because now we're working in space-time, right? We're not working in just a single spatial variable. Okay? But everything works out the same. Just notice that the arguments of these exponentials are dot products between four vectors. Okay? And that'll come back. Okay? We'll see how it works. All right? So what I'm going to do is I'm going to take phi and replace it with this guy. Right? And why do I want to do that? Because I have this del squared here. Right? And if I just had del squared operating on phi, I don't know how to evaluate that. Right? But if I take the Fourier transform, the only spatial or space-time dependence is in the exponential. So then I can take that del squared, okay? And it's going to pull down a factor of ik squared, right? And this is just, like I said, this is just reminding you that those guys are products of four vectors, okay? All right, so we'll take a Fourier transform, and we'll do the same things that we did before. So, to be completely general, we're going to symmetrize that source term, right? So we replace j phi with 1/2 j phi plus j phi, right? But those guys are allowed to have different arguments, okay? Or they will have different arguments. Then we plug in the Fourier transform, and like I just said, the del squared is going to pull down a factor of it's going to pull down a factor of ik squared, right? And that's going to give you a minus k squared. And we'll do some algebra, right? And what we would find is that now we can pull out an exponential. Remember before it was e plus e prime t, right? And that allowed us to do the t integral. Here it's a space-time point, so it allows us to do the four-dimensional integral, and it gives us a four-dimensional Dirac delta function, okay? So then that delta function allows me to go back and do one of, where am I? I got lost for a minute. Allows me to do one of these guys, right? One of these integrals, or one of these, right? Delta 4 because I'm plugging in. Yeah, I got typo here, right? So this guy, phi of x. So this should be an integral over k, right? Everybody agree with me? Yeah. Okay. So that's going to allow me to do, when I get that Dirac delta function, it's going to allow me to do that integral, one of those integrals, and that sets k prime to say minus k. So if you go back and look at what we did before, that was the point where it let us set e prime to minus e. Okay? All right, so now I've gotten down and done all this stuff, and I get down to an expression that looks like this. Okay? And remember that we're always shifting the Hamiltonian or the Lagrangian by these I epsilon terms, okay? But I'm not showing them here. Just remember, usual, it goes just like it did before. So anywhere you see m squared, you know that it's really m squared times 1 minus I epsilon. Remember that replacement that we talked about? Okay. All right, so just know that it's always there, okay? And that's where, if you had to put it in by hand, at this point, if I asked you, where's the I epsilon, you'd say it's inside that term, k squared minus m squared. All right, so in other words, okay, so let me be explicit here. So we would have minus phi twiddle k, right? And then I have k squared minus m squared, and when I have phi twiddle minus k. Right, but I say, where's the I epsilon? Well, the I epsilon's here, right? So it's minus phi twiddle k, right? K squared minus m squared 1 minus I epsilon phi twiddle minus k. Okay, but then I use the same argument that I did before, that this is a constant, right? And it's multiplying this thing that I'm going to set to 0. So what I can do is just absorb that into that guy, into that epsilon, right? And so if I ask, you'd be able to say, oh, this I put in my epsilon, I epsilon is going to look like that. Okay? Okay. That's just because I'm just trying to be explicit right now, because I epsilons will come and go, like particles in and out of the vacuum. Okay? They come in and go. They come in and leave whenever you need them to come in and leave. Okay, but they're always there, right? But then the reason that we want them there, that we have to have them there, is because we want that simplifying feature where we're computing these time-ordered products in between the vacuum states, right? That simplifies our life a lot. Okay, anyways. All right, so we've gotten it down to the point of equation 6, okay? And now what we want to do is we want to try to simplify things. And we're going to simplify things by doing a complicated looking change of variables, okay? But when we do this change of variables, we go through the same exact steps that we did before, right? And we found that a bunch of stuff cancels out. And what we end up with is something that looks like the piece is going to look something like this. So it's going to look like the action without any source terms, okay, being multiplied by a piece that only has source terms. Right? You guys remember that? Do you remember that result? Yes, no, maybe? Okay. Let me pull it up, because I'm skipping major steps here, but I want you to make sure that everybody's on the same page. Okay. All right. So this is where we got to this point. So here, remember this step in the harmonic oscillator? We got to this point where when we did this change of variables, right, we had this term that only depended on f twiddles and the term that only depended on x twiddles. Right? So now for us, x twiddle in the field theory case is chi. Chi twiddle. It's our new variable. Right? And f twiddle is obviously j. And so we get the same thing that we had before, just replace e squared with k squared. And so that allows us to pull that piece outside, right? Because it doesn't have any x dependence in this case, or in our case, it doesn't have any chi dependence. Okay? And so at that point, we said, well, this second line of equation 63 is just 1. Right? So our full path integral is only that top line there. Okay? So now let me go back to the field theory case, right? And that's what I'm saying, is I do this change of variable, I go through the same algebraic steps, and I get down to something that looks like this. Okay? It's that term, the exponential term that only depends on the source terms, right? This was our f twiddle term, multiplying the path integral in the force-free limit. okay? And in our case, what we would call a source-free limit, okay? Everybody good with my analogy there, explanation? Okay, so I'm skipping a couple slides here, going from equation 7 to equation 8, but it's the same exact steps that we did before, okay? And so we use the same argument that, in the absence of forces or the absence of sources, this guy is just 1, right? The path integral with no source terms is just 1 when it's evaluated between the ground states, okay? So that allows me to replace the complicated looking path integral with this guy. It's just equation 11, right? It's just the nice little compact expression that involves these source terms, okay? And we're going to do the same exact thing when we want to compute correlation functions. We're going to take functional derivatives not with respect to f, but with respect to j now, okay? But first, let me take our Fourier transform and take the anti-Fourier transform, or the reverse Fourier transform, to get back to position space, right? And if I do that, I can do the same thing I did before. I can pull a lot of this stuff into this nice, harmless-looking function that we call the Feynman propagator. Okay, this delta x minus x prime is the analogous, or the analogy of our g function, our Green's function, right? It's the Green's function for the Klein-Gordon theory, Klein-Gordon field theory, okay? Right? And so it's defined like this, okay? Equation 13. And like I said, it's called the Feynman propagator, and it's just the Green's function, and that's all that, okay? And like I said, there's no reason to compute this guy, and we'll see why in a bit. I kind of hinted at it last time, that once you get to this point of, let's say, equation 11, and you start taking functional derivatives, you start noticing a pattern, because it's going to pull down factors of this propagator. Right? And this propagator is called a propagator for a good reason, because it takes you from one space-time point to another space-time point. Okay, and just to give away the spoiler alert here, these guys are called source terms because they're going to create a particle. They're going to create a particle at space-time point x prime. And then this guy, the propagator, is going to take me from x prime to x. Okay, and then this guy is going to, it's like a anti-source term, so it's going to annihilate the particle. Okay? We'll get to that, but I just want to, so you understand where I'm coming from with some of the terminology. I just need a coffee like IV. I can just wheel around one of those. I'm running on fumes here. Okay, so like I said, time-ordered products of operators. Now remember, our operators are not the capital Q's, they're the phi's, okay? And so if I want to bring down factors of phi, right, think about how we wrote the original Lagrangian. So let me just go back, show you. Right, so if I want to bring out factors of phi, right, on the right-hand side, phi is a number, right? It's like an eigenvalue, right? And so if I want to bring down factors of phi, I want to hit this thing with functional derivatives with respect to j. Okay? So if I want to build time-ordered products of operators, so now on the left-hand side, phi is an operator, right? So it's, like I said, you'll know it from its context. You'll know, that was the word I was looking for, context. You'll know if phi is an operator or a number, okay? So if I'm interested in computing that correlation function, or that time-ordered product of operators, or that endpoint function, or whatever name you want to give it, I just take functional derivatives of my generating functional, okay, the z0, right? It gets a little cumbersome, to put it lightly, because now you're dealing with, all these functions, they're not just like little discrete, numbers or functions now. Now everything's a field or a function or whatever, right? And you're integrating over all this shit, okay? So what you have to do is you have to introduce some simplifying notation, okay? So I'll introduce the notation like this. So phi sub I means phi with argument x sub I. Okay, and then the same thing for j's, the same thing for the deltas. Okay, and then yeah, so for the deltas, and then when you see any repeated indices, right? This is like e to the I action, right? And you know that e to the I action, there's an integration in here. So anytime you see these repeated indices, you know that there's an integral. So for this first line here, there would be two integrals, 1 over x and 1 over y, right? Because it's coming from this guy, which one? It's coming from equation 12, right? So if I had to, I would write this as e to the I over 2, j sub x, j sub x, delta sub x, x prime, j sub x prime, with no integration. Everybody see? Okay. So it's just introducing shorthand notation, so I don't have to write all these freaking integral signs. Okay. All right. Okay. So let me rewrite. So so basically equation. What did I say it was 12? Yeah. So equation 12 is the thing that's being hit by these two functional derivatives. Okay. So you see how nice it is. Okay. And so when you start doing these things, right, it's going to pull down factors of this stuff, right? So you can see that when I take the functional derivative with respect to J2, I'll have two terms, right? I'll have a term where it hits this guy, and then a term where it hits this guy. Okay, so you see, and you know that when it hits this guy, it's going to give me a delta function that sets x to 2 or 2 to x, right? And so that's why this delta here, the capital delta, has our subscript 2 now. Okay, so this comes from hitting this guy, and then this would hit this guy, and so here I have x2. Right, and then I get the exponential back. Everybody with me? Yeah. Okay. All right, and then I would hit it with x. Then I would hit what's left with the J1 functional derivative. Right? So now I'm going to have multiple terms, right? So I'm going to have J1 hitting this guy, right? And it's going to leave me with a delta, right? I have a J1 hitting this guy, it's going to leave me with another delta, right? And then I'll have J1 hitting this exponential, and that's going to have leftover J's, right? If I have leftover J's, then I know that I can get rid of those. All right, so in the end, so here's the next step I was explaining, right? So I get one term that goes like delta, let's go back. All right, so when I hit this guy, I'm going to have one term that goes like delta 2, 1, and one term that goes like delta 1, 2. But those are the same. They're symmetric, right? If you go back and look at how they computed Green's functions, they're the same, so you can combine them and call them delta 1, 2, or delta 2, 1. So that's that first term there. Right? And now you see that everything that's left over has a factor of j in it. Right? But I know that I'm setting j equal to 0, and so I can just drop all that crap. Okay, so that's what I'm saying, that when you go through, and if I gave you the time order product of 3 operators, you would get what? Huh? Right. Good. Yay. So, all right, so you get 0. But if I did 4, if I ask you for 4, you're going to take all these derivatives, and you'll start to see that, oh, when I come back to this term and I hit it with another functional derivative, I'm still going to have a leftover j. You know what I'm saying? So there's no point in me keeping that term around because I'm always going to get a j out of it, right? So I can just drop it, okay? All right. Okay. So in the end, when you do this time order product of 2 operators, or the 2-point function, or the correlation function, or the, am I forgetting one? Anyways, when I compute this time order product of operators, I get one delta function, one Green's function. Not a delta function. It's a Green's function, but it's a delta 2, 1. Okay? All right? So This, do I actually do it? Or do I? Yeah, I actually do it. Okay. So, so let me just kind of scan through this. Okay, so I'm doing the case of 4 operators because this is what we really want, right? This is what we're interested in because we're looking at time ordered product of 4 operators, which are going to give us 2 to 2 type scatterings. Okay, and that's what we're primarily going to be interested in. All right, so I would have 4 functional derivatives, right, acting on my path interval or my generating functional. Okay, and so I carry all these derivatives through. I'm not going to go through this step by step, but the end result is you get something that looks like this on equation 9 or slide 9, right? And I take one more functional derivative, okay? But I can see in here that there's a lot of these terms in here. Even after I take, I can tell that when I take this guy on this, I'm still going to have this j left, right? So why the hell would I even bother, doing that when I know I'm setting j to 0? Okay. Anyways, I did it anyways, just to show you. Wow, I used to be a lot more energetic than I am now. Okay, but in the end, when you set j equals to 0, you end up with a sum over pairings of these Green's functions. Okay, so this should sound familiar because it's the same exact thing that we found for the simple harmonic oscillator. Right there we had g's. Okay, all right, but it's the same deal. Right, it's the same thing. You get these sums over these pairings. Okay. Right, and you can represent them just like we did before. And the name I couldn't think of, this is called Wick's theorem. That's what I couldn't think of last time. So when you have a time ordered product of operators, you can go through and you can do these functional derivatives, or you can use Wick's theorem and say, I know that the end result is going to be just summing over the pairs of these guys. Okay? Or summing over the different pairings. Okay. All right. And like we said, that anytime we have odd numbers of fields, it always vanishes. Okay. Okay. So let me see where I'm at. Okay. We'll take a couple minute break now, and then we'll come back to this. Okay. I don't know if I'm going to be able to go for the full time today. I'm running out of juice, but let's take just a few minute break, and then we'll come back and finish this up. Okay. Anybody see my email from earlier today? Did you get it?
It's on the website.
So you saw the email about the website?
No, I just saw the website.
Okay.
It's like one of my bookmark tabs.
Okay. Yeah, I was playing around, but did you get an email from me? I'll go back and double check. But anyway, so I'm publishing. I'm changing where the placement of the website. I'm using Google Drive, so there's a link now because it's just a lot easier than having to try to but so I'll double check. But I thought I sent an email to everybody. I wonder who I sent it to. Yeah, they're really confused right now. I've seen two second and third grader little girls walk around like phones just chatting it up. And,
$600 replaceable object.
yeah. All right, let's get this over with. Okay. Okay, so before we move on, right? So this has all been for non-interacting theory. But before we move on, we could ask ourselves, how can we physically interpret what all this means, okay? And so a lot of this won't be completely clear, but it'll hopefully become clearer as we move along, okay? And that's kind of, if you haven't noticed, that's kind of a theme in this class. Things might not be clear at first, but I'll try to drill them in your head a bunch of times, and then finally you'll just come to accept it, even if you don't understand it, just accept it, okay? So the way we interpret all this stuff is like I was saying. So these J terms, we call them source terms for a reason, because what they do, we'll see, is they basically create a particle out of the vacuum at a particular space-time point. Okay, so they'll either create a particle or they'll annihilate a particle. Okay, and what the propagator does, hence the name propagator, what it does is it takes the particle that you've created at point X and moves it, say, from point X to point Y, space-time point. Okay. So, and the way you see that this happens is look at the time-ordered product of two operators, okay? And while you're looking at this, remember what these guys look like, what the phi's, the fields look like in canonical quantization. Remember, they're kind of linear superpositions of annihilation and creation operators, right? So if this guy 5x1 is operating to the right on the vacuum state, the only contribution you're going to get is from the creation operator, right? And vice versa from this guy. When it goes to the left, it's going to, let's see, if it goes to the right, then what it's going to do is you're going to create a particle at x1, and then this is going to annihilate the particle at x2. Right? And on the right-hand side, you've got the propagator. The propagator, like I said, is moving that particle from space-time point 1 to space-time point 2. Right? So diagrammatically, if you want to think of this, by drawing pictures, if that's what, I enjoy pictures a lot more than I do equations, right? I can plot this, right? I can draw a diagram where I'll denote, you always want to denote, when you start writing down these diagrams, the flow of time, okay? Because remember, we're talking about time-ordered products, right? So in our case, well, in the general case, you'd want to sum over both cases. So where from time goes from x1 to x2, and then vice versa, right? Or it goes from x2 to x1. But for this case, this is where, let's just say we know that x2 happens after x1, okay? So diagrammatically, you could draw it like this, where the dots on the ends of those lines are the J terms. Those are the source and the sink terms, right? So you can see that, you're cruising along in time, there's nothing, and then oops, all of a sudden at x1, J creates a particle, right? And then the Feynman propagator moves that particle to some space-time point x2 where it's annihilated, okay? All right, so that's the two-point function because, we just had that one Green's function. Now, if you go back and you look at time-ordered product of four operators, you can see how you could represent this, this messy-looking thing when you think about what the deltas are, right? In terms of diagrams, right? So you have three separate cases, okay? One where the particles are created at, say, well, in this case, how did it go? I guess Yeah, well, I don't know. Don't worry about the flow of time. But I'm basically creating particles at two spots, moving them to two other spots where they're annihilated. Right? And so you have three different cases. The first case is where you go from 2 to 4 and 1 to 3. The second case is where you go from 1 to 4 and 2 to 3. Right? Notice that the lines, they look like they're touching, but they're not. Okay, take my word for it. All right? And then the final case. Okay? And at those endpoints, they're annihilated. And all of this can happen in three unique ways, right? So you have to sum over all the possible ways that this can happen. Okay. All right. So that's non-interacting. Let me just see how. Wow. Okay. So maybe we won't finish this today. Okay. So that's non-interacting theory. Okay. And what I want to do now is start to make the transition to a interacting theory, okay? And an interacting theory that we're going to study and that we're going to focus on a lot is phi cubed, what's called phi cubed theory, okay? So I'm taking the real Klein-Gordon theory, free theory, and I'm adding on to it an interaction term, and the interaction term goes like phi cubed, okay? There, you have a couple, Phi cubed. That's what I'm getting ready. That's what I'm getting ready to say. So the normal thing that people do is to not study phi cubed theory, but study what's called phi fourth theory, lambda phi to the fourth theory, and to study that in 4 dimensions, 4 space-time dimensions, which seems completely reasonable. It's a renormalizable theory. It has all the nice features that you want. Okay. The problem with phi cubed theory is that it's not renormalizable in 4 dimensions, okay? But it is renormalizable in 6 dimensions, okay? All right. So, so lambda phi to the fourth theory. If you go and look and say Peskin, he studies lambda phi to the fourth theory, okay, and in 4 dimensions. It has nice applications because anybody know why? Well, yeah, we live in 4 dimensions. But no, the Lagrangian. What does the Lagrangian describe? Lambda phi to the fourth describes a particular particle that was just discovered a few years ago. It rhymes with Schmidt's. The Higgs, right? The Higgs is an example of well, it's a complex field, but it's a Klein-Gordon Lagrangian plus a lambda phi to the fourth term. Okay. We're not going to do that, okay? We're going to move into the 6th dimension, okay? And we're going to study phi cubed theory, okay? And the reason that we do that is the same reason that Srednicki does it, is because it's a nice toy model where you can study almost every aspect of quantum field theory, just in terms of scalar fields, okay? So you can do all this cool stuff with just scalar fields if you work with phi cubed in 6 dimensions. If you work with phi to the fourth in 4 dimensions, there's some aspects of quantum field theory that don't come in, okay? And so you have to wait until you get to particles that have spin, right? But as soon as you add spin, everything goes to hell and it gets hard, okay? So what we try to do is use this phi to the cube theory and work in 6 dimensions. It's not we obviously, well, maybe we do, don't live in 6 dimensions, right? And we don't have any examples of any phi to the cube type interactions in real life, but it gives us a chance to play around with this and to develop all the formalism. So then when we go to, first we'll talk about spin 1/2 particles, fermions. We'll be able to apply a lot of this stuff that we've learned from this semester. We'll just be able to say, oh, we're going to do this. And you're going to be like, oh, yeah, of course we can do that, right? Instead of having to develop all this stuff with spins included, okay? Okay, so that's my spiel, okay? So that's why when you look in Srednicki, the first half of the book is nothing but phi cube theory. But if you look in Peskin, you see he doesn't talk about phi cube theory, he talks about phi to the fourth. All right. So it's all the same stuff, but anyways. Okay, so we're going to work with this particular theory, okay? And we want the LSZ formula to be valid, we want it to still apply to an interacting theory. So that means we have to ensure two things, right? One, that the vacuum expectation value or the VEV of the field vanishes, right? Because we know that it does in the non-interacting theory, and that the single particle states have the correct normalization, right? So these are our two conditions. We write down this Lagrangian, then we have these two conditions, okay? And to ensure those two conditions, I can, in general, shift the field by the VEV, right? And that'll ensure that even if this guy is, if I compute it, if it's not 0, this guy is going to cancel the VEV off, okay? And so it would give me 0. And to ensure that we have the correct normalization, I can scale the field, right? And both of these don't affect the physics, okay? And we talked about that a couple lectures ago, okay? All right, but so when I do that, and I plug it all in, and this is a good exercise, is to make the, take this Lagrangian and make those replacements, okay? And to see if you can get the correct form, right? So we would do all those changes, and we would get a form that looks pretty similar to what we had before, except it has these counter terms, okay? So they're just combinations of the VEV and the rescaling factor, okay? All right, but these are the guys that we're going to compute, okay? So these are the guys that we compute to ensure that, the VEV remains 0, the single particle states have the correct normalization, okay? But we have this one extra term that we talked about that's kind of weird, which is that single phi term at the end, okay? But we'll get to that. And then we talked about, we also mentioned that we have 4 unknowns, right? The 4 counter terms, the 3 z's and the y, but we only have 2 conditions, right? We only have the VEV condition and the single particle condition, and so that means we have to rely on experimentalists to give us the other 2 conditions, which are the value of the mass of our field, right, our particle, and the value of the coupling, okay? And so that gives us 2 more conditions, and we'll see how we use those values to determine these counter terms. Okay. All right. So we're going to do what we did, what we talked about before with the simple harmonic oscillator. Right. So I'm going to rewrite the Lagrangian in terms of a piece that we know how to solve, or a piece that we know what the path integral is. Right. Plus some small piece. Right? And then I'm going to use the idea that I can build this small piece by taking functional derivatives. Right? So it's going to depend on, function. It's going to depend on, in our case, it's going to depend on factors of phi. Right? So in this case, look up here. So our interaction term goes like phi cubed. So that means the interaction Lagrangian is going to be something that goes like phi cubed. So how many functional derivatives am I going to have to take? 3, right? To build a phi cubed term, I'm going to have to take 3 functional derivatives, right, of this guy. And this guy is just what we already computed, right, for the real Klein-Gordon field. Okay? This is the non-interacting piece. Okay? We already have an expression for that in terms of the J's. Okay? Right. Okay, so that's how we're gonna build it. Z1, the 1 on here, lets us know that we're working in an interacting theory. Okay, so you see over here, the 0 is non-interacting theory, the 1 is interacting theory. Okay, so that's the notation that we use. And you say, well, wait a minute, why? Before we had this thing was equals to that. Why is it now turned into a proportional? Well, we'll see why. Okay, and actually. It comes about because when we apply this I epsilon trick, when we shift the Hamiltonian or the Lagrangian, we screw up the equal sign. Okay, and so what we have to do is go back and fix that. Okay, just like we have to go back and fix things, using renormalization. Okay, but we'll fix it later. Okay. Right. So for our particular case, the phi cube theory, like we said, the Lagrangian we're going to build by taking 3 functional derivatives. So this is what it's going to look like, okay? So I'm plugging in, I've got 3 functional derivatives, and I've got my constant factor and then the counter term factor in there. And you can convince yourself that if I take that guy and I operate on what I had before, I'm going to end up getting, you know, a Lagrangian that's going to look like that. It's going to be sitting inside the exponential, but you're building it, right? Because the z0 has this form, okay? And so if I say, okay, you know, we're going to treat this as a perturbation, so let's go off and compute things to first order, right? We compute things to first order in the coupling constant, just like we would in normal perturbation theory. You know, we calculate things to first order, and then we would go and compare it to the experiment. It would be off a little bit. We'd blame them. They'd blame us. You know, we'd have to slap them around a little, and then we'd realize, oh, maybe we just need to go to higher order in perturbation theory. So we go and we compute the next order term, right? And the next order term would be like phi, you know, like a phi to the 6th term. We'd have to take 2. It would be the next term in the expansion of that exponential there, okay? All right, so what we want to do is plug that in and start taking functional derivatives, okay? And that'll give us, basically we'll compute the scattering amplitude, okay? So before doing that, you might ask yourself, why is Fat Albert on this slide? Does everybody know who Fat Albert is? Do you guys have Fat Albert in your own? I doubt it. Okay. So Fat Albert was a cartoon in the 70s. Okay. And so it was the Fat Albert gang. It was Fat Albert, who's that guy right there. It's Bill Cosby. Do you know who Bill Cosby is?
Yes.
No? Okay. That's all right. So there was this gang, and they would have, you know, they would always get into these hijinks and things like that. But Fat Albert always had a saying that, you know, in the middle of all this stuff, be careful because you might just learn something. Okay, that was kind of his catchphrase. And so I was like,
hey, hey, hey.
yeah, he said, hey, right? We'll have to have a day where I'll show some YouTube videos of Fat Albert and all the other references that I'm using here. But Fat Albert always said, you know, be careful, you might just learn something. So what we're going to do is we're going to take the Fat Albert approach and not try to tackle this head on, but to consider an easier problem and, you know, see what we can learn and then come back to this harder problem and try to apply that. And honestly, I'm running out of juice. I think what I'm going to do is just stop here and we'll pick it up because we'll pick it up on Tuesday. Okay. Yeah, because yeah. So let's just cut it. We'll cut it short today because I'm about to pass out, and we'll pick it back up. And actually, we're going to study something that looks a lot like phi to the 4th theory. Okay, but it'll give us an idea of how to go about how to compute these things. Okay, for phi cube theory. All right. Okay. All right. Well, have a good weekend, and let me know. Like I said, I'll try to send that email again. I don't know. Nobody got an email from me from today. Okay. I don't know. Maybe one of those.